Okay. All right, so here we go. So the ideal gas law is ideal because it includes all variables. You are now able to solve for moles in addition to pressure, volume, and temperature. So what makes it even cooler is that you can find much more than just those variables. So if you recall, if I asked you to solve for the number of moles, like if I said, oh, you've got 10 grams of carbon, how do you convert that to moles? Well, you guys know that if you take the mass and if you divide it by the molar mass, the result is moles. So therefore, N can be solved if you have grams divided by molar mass, right? So the mass in grams, and of course, mm is molar mass. So because we have a formula, PV equals nRT, PIV-NERT, for the ideal gas law, N can simply be substituted for. So to do that, you literally just take this and you direct substitute to give this. And so now we have a variation of the ideal gas law, which includes the molar mass and it includes the mass of the sample. So if I can rewrite this to kind of be clearer, PV is equal to mass times R times T over the molar mass, right? Just to kind of show that RT is indeed multiplied by G, right? But we are dividing by molar mass. So with this second version of the ideal gas law, we can just rearrange, and by rearranging, we get this form here. All I did was multiply both sides by mm and divide both sides by PV. And then we get the Homer-Simpson equation to solve for molar mass. Because as Homer would say, great PIV. I don't know how many of you watched The Simpsons, right? Anyways, this is rearranged to solve for molar mass. And being able to solve for molar mass for a gas is very useful. It allows us to narrow down and help us identify mystery substances. So, it's okay, so there's Homer saying, Okay, anyways. Now that we have the equation rearranged, we can just go ahead and solve for the molar mass in this problem here. So what do they tell us? They tell us that we have a cylinder of a gas that has an illegible label. Hard to believe, but yes, it happens. There are bottles sometimes where the labels fall off. So we have to figure out what's inside them. So let's take what we know. Volume, 300 milliliters, right? 300 milliliters, we need to convert this to liters. So .3 liters. 685 torr. We need this in atmospheres. Remember, the ideal gas law is very unit specific. You have to have the prescribed units. All right. Oh, you know what? Temperature is not given, but that's okay. We will just use standard temperature. What is standard temperature, guys?
It's like 0 degrees Celsius.
0 Celsius, right. So 0 Celsius, which is 273 K. All right, let's plug in what we have. the grams, the mass, and R is 0.0821 liters times atmospheres over moles times Kelvin. Temperature 273 Kelvin. And pressure 0.901 atmospheres. And volume 0.3 liters. All right. Times 0.0821 times 273. So when I calculate these, I like to just multiply everything by the top. And then I divide by 0.901. And then I hit divide by 0.3. So this is what it looks like. Right, what I entered in. Okay, so the molar mass of this gas is 1,202. Let me just double check that one more time. It seems a little high. That was way high. That was not right at all. I take that back. The molar mass is 120. Okay, but what are my units? Let's go to the unit examining red pen. All right. It's Kelvin being divided by Kelvin. Liters divides liters. Atmospheres divides atmospheres. The only units left, let's get some contrast here, are grams being divided by moles. Grams per mole, which, if you recall, is the unit that we use for molar mass. But Mr. Park, there's a lot of writing when I have to show all of these units. Do I really need to do that on a test or quiz? Well, only if you want all the points. However many points you want to get is up to you, but I won't give you all the points unless I see all of those units canceled just like I've shown. Okay, I hope we've driven that home. I hope that's something that is understood by now. Okay. Are you guys okay with taking the ideal gas law, substituting in moles, and giving us a new version of the equation? I will take your silence as a resounding yes. Okay, but wait, there's more. If I take the equation that we just, if I take Homer's equation, sounds very mathematical, doesn't it? Homer's equation. It makes me think like high-end math, like a Euclidean formula. Homer, like the Odyssey. No? That's right, English. Yes. Yeah. If I take Homer's equation, there's something else I can get out of this. You see, back in Unit 1, we studied density, and density is defined as mass over volume, right? But mass in this case, in Homer's version, is grams. So when I look at Homer's equation and I see grams and volume, that means this equation includes density as something that can be solved for. All I have to do is isolate the G over V. So let's just do some manipulations here. I can multiply both sides by P, divide both sides by R and T, and I get G over V is equal to pressure times molar mass, which is divided by R and T, right? And this is known as gas density, the G over V part. Which is also just as useful. So, if we needed to find the gas density, we just use the ideal gas law, and we plug in what we have, but we need to make sure that we've arranged it the right way. Okay, so, this problem is not actually asking for density. That's okay. We'll do one solving for density right after this. All right, so this problem right here says the density is 1.23 grams per liter. They're giving you a temperature, they're giving you pressure. What is the molar mass? Okay, so let's solve for molar mass since we're here. All right, so molar mass is equal to G times R times T over PV. Okay, so they are giving me 1.23 grams per liter. 1.23 grams per liter means I have 1.23 grams and I have 1 liter, right? So this is G and this is V. So I take those two values and I plug them in. 1.23 grams, 1 liter. Okay, does that make sense? I know it seems like they're only giving you one value, but they're really giving you two for this equation because the volume is 1 liter. All right, but we got to fit in the rest of the stuff. All right, so the value of R all right, temperature is 80, so 273 plus 80, so 323. And the pressure is already in atmospheres. All right.
It's 353.
Sorry, thank you. 353. Speedy math equals bad math. All right, let's. All right, 32.4. Okay. Unit pen, here we go. Kelvin, Kelvin, atmosphere, atmosphere, liter, liter, grams per mole. Okay. So do you guys understand, if you are given a gas density, they're giving you the mass in grams and the volume is 1. Okay. All right. I'm going to add a page here to give me some more room to work because I want to give you guys a problem where you solve for densities. So okay. We have volume, a tank with a volume of 2.5 liters. All right, the pressure is 3.2 atmospheres. Let's see. And the temperature, 25 degrees Celsius. So we'll go with room temperature. Actually, take that back. Let's ignore the volume. I want you to find density, so you're not going to need the volume. So the gas is what we call ethane. Find the density. Does it seem like you're missing something? Did I not give you enough information? What do you have to do here in this problem that was not explicitly stated? The volume is part of the density, so no. You'll get that when you get the answer.
The molar mass?
Yeah, I gave you the formula. You need the molar mass, right? Because Homer's equation includes molar mass. I did not give you the molar mass, but I did give you the formula so you can find it. All right. What do you guys have? Okay, Holden, that is correct. So pressure was given 3.2 atmospheres. The molar mass you had to figure out was 30.08 grams per mole. All right, so gas constant 0.0821 liters atmospheres over moles Kelvin. And our temperature was 298 K. All right, unit pen says atmospheres over atmospheres, 1 over moles over 1 over moles, so the moles part actually cancels, kelvins cancel, and you're left with grams over liters. And the answer, after you calculate, was 3.93. Everybody get that? Good. All right. Okay, how are we doing? Ideal gas law, variations, either using molar mass or using density. Okay. I'm going to take the second here to interject and remind you that we have a quiz next class. All right, so today Tuesday, so your quiz is Thursday, right? And it goes up to the ideal gas law. So there might be a molar mass or there might be a density problem on here, okay? I have one more topic to go over that's not going to be on the quiz. That's the next page on notes, and it's called partial pressures. So, partial pressures, Dalton's law of partial pressures. It's kind of a simple law. It's kind of silly that it's a law because all it says is that when you have a mixture of gases, and that's assuming that they don't react with each other, hence non-reacting. If you have a mixture of gases, the sum of their individual pressures equals the total pressure. Okay, so let's say you have a scuba tank, and in the scuba tank you've got oxygen and nitrogen. Well, what that means is the oxygen that is caused by or the pressure that's caused by the oxygen plus the pressure caused by the nitrogen, that's the total pressure in the tank. And if there were more than 2 gases, then you would add another pressure, right? So depending on how many different gases there are, each one has its own pressure. That's what we call partial pressure. Pressure for an individual gas. Okay, so partial pressure, total pressure, not the same. You guys know that air is made up of more than one gas, right? Right? Air is nitrogen, air is oxygen, but there's also a little bit of carbon dioxide, there's also a little bit of argon in air. So air is a mixture of partial pressures. The total pressure at sea level is 1 atmosphere, right? But in reality, air pressure is like 0.8 atmospheres nitrogen, 0.19 atmospheres oxygen, 1% and 0.1 other. Okay, so if you understand partial pressures and total pressures, then this is something that will come up. We might ask you to solve for what's called a pressure fraction. And literally all it is the pressure of one part over the pressure total. Right? That's all it is. And it's going to equal a decimal value. 0.2, 0.7, 0.9, 0.5, just, whatever it is. Similarly, you will be needing to find what's called a mole fraction. And the mole fraction is the same idea, but with moles. So it's N for an individual divided by the sum of moles of gases. Now, what you learned last class from Avogadro's law is that moles and pressure are proportional, right? And volume is proportional as well. So what that means is that the pressure fraction is indeed equal to the mole fraction. And this is going to be very useful because sometimes you need to figure out how much moles you have in something. You don't know the moles, but you do know the pressures, or vice versa. Okay, so example. Let's say we have a 6-liter tank. And in this tank, let's say we have this much oxygen and this much nitrogen, and this is the temperature. What is the total gas pressure in the tank? Actually, total and individual and partial pressures. I want to know the individual pressures and I want to know the total pressures. Okay, so let's take our information and put it into terms that's useful. So 75 grams, let's turn that into moles. All right, so I've got moles of both gases. So let's use the ideal gas law. And so, here, I'll color coordinate this. So back to green. For oxygen, the pressure will be the moles, 2.34. All right, here's where we got to get squinty. R temperature 298 K. I did not leave myself enough room. And the volume 6 liters. So the pressure from oxygen is 9.54 atmospheres. Okay, so the pressure of nitrogen and you know what? These values here are all the same because they're in the same container, they're at the same temperature. Right, so, and R is the same, so I'm just going to take my 8.04 moles and multiply it by R, multiply it by 298, divided by 6. All right, so we've got our partial pressures, and so they want to know the total pressure. So P total, 42.3 atmospheres. Now, of course, we can check this, right? Because we can take the moles. We can check and see that the pressure fractions are indeed equal to the mole fractions. So, for example, Let's take nitrogen, P of nitrogen, or the P total. Right, well, that would be 32.8 atmospheres over 42.3. So the pressure fraction is 0.775. And just to verify that mole fraction and pressure fraction are equal, let's take the moles, so N of N2, which is 8.04, and divide it by N total, which is 10.38. Oh, look at that. The pressure fraction and mole fraction for nitrogen are the same. Okay, so it's a relationship. It's fairly straightforward. The key point, right, is that the sum of all individual pressures equals the total pressure, and that mole fraction equals pressure fraction. If you remember those two things, you'll be able to solve a lot more problems. Okay, one last thing to go over, and this is applying Dalton's law. This is called gas collection over water. So this is kind of tricky. So I'll go slow here. You know what? I need another page. All right, back to the insert page function. What happened? Oh no, I put it in the wrong place. All right, let's try that again. Okay. This is going to draw on some past knowledge. Do you guys remember when we did a reaction where we had magnesium and we added it to acid, and then we took a test tube and held it upside down over it, and we collected the hydrogen gas?
And then set it on fire and it popped.
Right. And then we lit it with a match and it popped. You guys remember that? So in this test tube above, okay, so this test tube in the top, there's hydrogen gas in there clearly because, you know, the hydrogen is floating upward. But what else is in that test tube?
Outside air.
Yes, air. There's also air in there. And remember how it popped? Well, why did it pop? Because hydrogen reacted with oxygen. Okay? So, if I wanted to collect a certain gas, then holding a test tube over another test tube is not a good way to do it, because you end up with more than the one gas you tried to collect. That test tube is a mixture of hydrogen and oxygen, but what if I wanted to collect just hydrogen? What I would have to do is have a reaction take place. So a reaction taking place in some kind of bulb somewhere. And then what I do is I take a hose and I dip the hose into a sink or a trough or some kind of bin or some kind of bucket. And this bucket is filled with water. Okay? And then I take a bottle filled with water. I take a bottle filled with water and I cup it with my palm, and I turn it upside down so the water doesn't spill. And then I lower that bottle into the bucket. And once the opening is submerged, I can pull my hand away and the water will stay in the bottle. Right? So this water that's in here stays in here because there's air pressure pushing down and that pushes the water and keeps it in the bottle. Do you guys ever see one of those pet feeders? Like you go away for a week and you have to give your cat water. So you get this giant jug, you turn it upside down in a bowl. And then every time your cat drinks, it makes that glug, 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 glug sound, right? It's the same idea. This is exactly just like that. Okay? So, first and foremost, does this design make sense? You've got a bucket of water, you've got a bottle filled with water that's submerged, and you've got a hose leaving from a reaction vessel. So what happens is this. I'm going to use a different color here. The reaction produces a gas. The gas bubbles through the water and collects in the bottle, right? And as it collects, there's now gas pressure in the bottle. The collected gas, of course, exerts pressure. And that pressure pushes the water down out of the bottle. And the more gas you collect, the more water gets pushed out of the bottle because the pressure inside the bottle is greater. Does this process make sense? Now, getting to the critical part. What you will do is eventually the water level on the outside of the bottle will equal the water level on the inside. Okay? This is critically important right here. So the water level outside the bottle equals the water level inside the bottle. And that means the pressure inside the bottle is equal to the pressure outside the bottle, and the pressure outside the bottle is known as barometric pressure. Right, just like a manometer, right? If they're pushing equally, then the water level is the same on both sides. So, this is useful because now we know the pressure in the bottle. Because it's the same as the barometer reading. But there's one catch. And the catch is that in the bottle, you actually have more than one gas. You have water vapor as well. Because water vapor, think about what's happening. You've got these bubbles pushing through, and water, anytime there's a liquid, there's going to be some evaporation. So there's just water that has evaporated. So your pressure is a mixture of two gases. The gas you were trying to collect and water vapor. So what that really means is that P pressure of the air is equal to the pressure of the water vapor plus the pressure of the gas that you're trying to collect. And the pressure of the gas that you're trying to collect is generally what we're trying to find. So very simple algebra, guys. How do we solve for the pressure in the gas? How do I rearrange this equation to solve for the pressure of the gas that I'm trying to collect?
Minus the pressure of the water on both sides.
Right. Right. So if I subtract the pressure of the water from both sides, that is how I find the pressure of the gas inside the bulb. And you know what? The pressure of air pressure, is always known. It's always a given. So the pressure of the water vapor is very simple to find. This value is just found in a table. Like there's a list of pressures of water vapor, and it's going to be based on temperature. All right, that was a lot. Let me back up and make sure we all understand this. When you collect gas, collecting gas just with an open vessel is no good, right? This is fine if you're doing fun experiments to see reactions, but you're not collecting the gas that you need. In order to collect gas we collect gas over water, and that's this process here. It's called collecting gas over water. So you take a tub or bucket, you take a bottle filled with water, you turn it upside down and submerge the opening, and then you let the reaction go, and then the gas bubbles. It bubbles into the bottle. The more gas you collect, the more pressure builds up, and it keeps pushing the water level in the bottle downward. Eventually, you get the pressure of the water inside the bottle and outside the bottle to be the same. When that happens, you know the pressure in the bottle is equal to the pressure of air. But the thing is, you must understand that the pressure in the bottle is actually made up of two gases, the gas you're trying to collect and water vapor. So you have to adjust for the water vapor by subtracting the water vapor from the air pressure. And that's how you get the pressure of the gas. And once you get the pressure of the gas, you use this value in the gas laws, like the ideal gas law. But you have to go through that first in order to get the pressure that you need to calculate with. All right? And again, this value here, the pressure of water vapor, is a given. It's going to be given to you in the problem, or we will give you a table that has the value in that table. You just have to look it up based on the temperature. Because it changes. If it's hotter, then the value is higher. If it's lower, then the value is lower. Okay? All right. So to tie this up, here's where we do an example. And I know this seems complicated, but in reality, the problem solving with this is very straightforward. Once you see an example, you'll feel better. Okay, so let's do this example here. Oxygen is collected over water at 20 degrees and 758 torr. Okay, so you are assuming, the assumption is that 758 is the total pressure. It's the atmospheric pressure, okay? When they give you the pressure of the bottle, that is the total pressure in the bottle. So, the volume of the gas collected is 350 milliliters. The vapor pressure of water, you see right here? Remember how I said that the pH2O is given to you? Here it is. So first question, what is the partial pressure of just the oxygen? No problem. P total minus pH2O is equal to the P of the gas. Okay, so 758 torr minus 17.54 torr. $740.46 torr. This is P gas. All right, so now we can answer the question. We want to find the moles and then the mass. Okay, so ideal gas law. Rearrange it to solve for moles. Make sure we have correct units, so I need to convert my torrs into atmospheres. All right, so we got our atmospheres, the volume 350 divided by 1,000, 0.35 liters. Temperature was given, 20 degrees, so that's going to be 293 Kelvin. Okay, so let's plug in what we have. All right, 0.0142 moles of O2 is the answer. And then, to find mass, we're just going to multiply by the molar mass. After we take that number and multiply by molar mass, we get 0.45 grams. Whew. Okay. That was a lot of talking, a lot of explaining for what is not really a difficult calculation. So collecting gas through water, it's just a subtraction. Just subtract the water vapor that you're given from what the total pressure is. And then once you do that, after that, it's just an ideal gas law problem. But I needed to explain, you need to understand why we're doing what we're doing. All right, so we're going to stop there. If you need to have this explained again, I recorded this lecture. I will post it in the lessons folder in Schoology. So let's stop. And your homework, we were going to do an activity today, kind of like a lab-like activity, and the homework. But I think, given how much we covered, maybe we're going to postpone the activity. We'll do that a different day. So what I just need you to work on is homework 4, which is molar mass and density using the ideal gas law. And you can start on that. And